So I'm doing a video for a last-minute section on 5.7 and 5.8 combined, in case anybody's absent during this critical time at the end of the semester, and in case anybody just needs to hear it again after class is done. So what we did before is we used complex numbers to describe solutions of quadratic equations. And now we're going to determine the number and type of roots for a polynomial equation. Now keep in mind that we're not going to use Descartes' theorem. I've cut that out of section 5.7. So if I happen to assign a homework problem that's around Descartes' theorem, please skip that one and go on to the next one. So you'll see where we're headed today. So zeros, factors, roots, and intercepts, and we've used these four terms interchangeably throughout the year. And so they're saying here that these four statements are equivalent, that if C is a zero of P of X, then we can also say that C is a root or solution of P of X. And we can say X minus C is a factor of P of X, and we could say if C is a real number, then C comma 0 is an x-intercept of the graph of P of X. So all this is saying, we could even say if, in this case, C happened to equal 8, if you want to see something more concrete, then those four statements could be made about that C is equal to 8. So if we consider this polynomial, x to the fourth plus 2x cubed minus 7x squared minus 8x plus 12, if we graph this on our graphing calculators, we're going to be able to see the roots, the zeros, the solutions, the intercepts right away. And those roots are occurring at -3, -2, 1, and 2. So we can say those are the zeros. Those are, so the zeros, those are the roots. And the factors would be x plus 3, x plus 2, x minus 1, and x minus 2. And the x-intercepts of the graph would be -3, 0, -2, 0, 1, 0, and 2, 0. So you are going to be able to use your graphing calculators to help you factor some of these polynomials, and they can be very helpful. You're going to have to know how to take your graphing calculator and translate that into the algebraic work, though. So it can be a tool that helps you, but you still need to be able to show me the algebra manually. So fundamental theorem of algebra, every polynomial equation with degree greater than 0 has at least one root in the set of complex numbers. So we're saying basically the degree of a polynomial equation, that's how many roots there will be. And some of them may be double roots, but if you have a fourth degree polynomial function, you're going to have 4 zeros. There might be 2 real and 2 imaginary, there might be 4 real, or they all might be imaginary. But you will have 4 roots to that equation. So if we want to solve x squared plus 2x minus 48 equals 0, state the number and type of roots, we would just start by factoring. We have a quadratic, so if we can factor, we'll do that. And I can see fairly quickly that this can factor to x plus 8 and x minus 6 equals 0. So we have 2 roots, and they're both real roots. So they're real rational roots. So -8 and 6 are the roots. So we have 2 real rational roots. And you could put that in your graphing calculator, and if you did that, you would see that it's crossing the x-axis at 6, and it's crossing the x-axis at -8, and you'd have a parabola that looks something like that. Solve y to the fourth minus 256. So I have 2 terms. I'm looking at that saying, do I have a difference of perfect squares? So do I have a perfect square in y to the fourth? And yes, I do. That would be y squared times y squared. And do I have a perfect square in 256? And I do. It's 16 times 16. So I have a difference of perfect squares. So I'm going to say y squared minus 16 and y squared plus 16 equals 0. Now when I factor that further, I can still factor y squared minus 16 one more time. That's a difference of perfect squares also. And that becomes y minus 4 times y plus 4. Now there's nothing else I can do with y squared plus 16, so I'm going to leave that here. It's not a difference of perfect squares, nor is it a sum or difference of perfect cubes. And now I'm to the point where it's fully factored. And then I can try to find my solutions now. Well, this factor is easy to see the solution. That's going to be y equals 4. And this factor, it's going to be y equals negative 4. Now this factor is slightly trickier. So we need to say y squared plus 16 equals 0. So y squared equals negative 16, and y equals plus or minus the square root of negative 16. So we're going to have two imaginary solutions to this problem. So we also need to say that we have plus or minus 4i. And now we see all four solutions to this equation. So a corollary to the fundamental theorem of algebra is a polynomial equation of degree n has exactly n roots, and that's what I've been saying in this video. So if you have a degree 5, it's going to have 5 roots. Degree 4 is going to have 4 roots. Degree 3 is going to have 3 roots. That does not mean it's going to cross the x-axis that many times, because again, you can have imaginary roots. So find all the zeros of f of x equals x cubed minus x squared plus 2x plus 4. For what we know right now, we're going to need to factor this, and we have 4 terms, and there's not a GCF, so we're going to factor by grouping. So I'm going to put these first terms together, and I'm going to pull out x squared, and that's going to give us x minus 1. So I'm going to continue my line of thought, but I realize I'm going to have to change what I'm doing here in just a second, because when I factor by grouping, that's not working for me. And so I'm going to have to find a new way to find solutions to this. So in this case, I'm actually going to go to my graphing calculator. And when I put this function into y equals in my graphing calculator, so there's our function, and I graph it, I can see that one of our roots is negative 1. And so in that case, I know that if a root is negative 1, then we have a factor of x plus 1. Now we're supposed to find all of the zeros. So I need to do synthetic division to finish finding the zeros. So I'm going to put negative 1 in the box, and I'm going to do our coefficients. So 1, negative 1, 2, 4. And so we get 1, negative 2, 2, 4, negative 4, and 0. And we should have gotten a remainder because negative 1 is a root of this. So when I write this, it's going to be x plus 1 times x squared minus 2x plus 4. And that's what this function equals. So this is where we can say, okay, we know that x equals negative 1 is one of our roots. But we have 2 more roots here in this quadratic. And when I'm looking at it, I realize I can't factor that. And so in order to figure out where our roots are, in other words, where this equation is equal to 0, we're going to have to do quadratic formula. And so A is equal to 1, B is equal to negative 2, and C is equal to 4. So let's plug into quadratic equation, and we get x equals negative b plus or minus square root of b squared minus 4 times a times c. So it's going to be minus 16 all over 2. So that's going to give us x equals, I'm going to get 2 plus or minus the square root of 12 all over 2. And simplifying that, we get 2 plus or minus 2 squared of 3 over 2. And this is where many of you made some careless algebraic errors. Let's pull a 2 out in our numerator. So we're going to get 2 times 1 plus or minus the square root of 3 Sorry, this was negative 12, so it's 2i squared of 3. Now it's I squared of 3. I lost my negative sign. And now those cancel. So our other two solutions, we now have that x equals negative 1 and x equals 1 plus or minus I squared of 3. So there's our other two solutions. Now, whenever you have imaginary solutions or irrational solutions, they're always going to be conjugates of each other. In other words, 1 plus square root of I squared of 3 and 1 minus I squared of 3, the only thing that changed was that middle sign. Remember from last chapter, that means that those are conjugates of each other. And that's what this theorem is. It says if a plus bi is a zero of the polynomial function, then a minus bi is also a zero of the function. And that's what we just found in the 1 plus I squared of 3 and the 1 minus I squared of 3. So this one's a little bit more challenging. Write a polynomial function of least degree with integral coefficients, and the zeros of which include 4 and 4 minus I. So we know that this has at least 2 zeros, but the fact that we have one of our zeros is an imaginary number, well, that complex conjugates theorem we just learned about says that the conjugate will also always be a zero of that function. So we actually have a degree 3. That's going to be the least degree that this could have. And so for our first factor, we'll use the x equals 4. So x minus 4 is the factor that would go with that. Now this gets into some fairly tedious algebra. So then the next factor we would say is, and I'm going to do green for this one, it's going to be x minus 4 minus I, because remember you always have to subtract that root from x to get the factor. And then the next factor is going to be x minus 4 plus I. Now you can multiply the purple and the green. You can distribute using the trinomials. I'm actually going to do something a little bit different than that. It would work either way. I'm not going to touch the x minus 4 yet. So we're coming up with a function. So be sure you give me an equation. So it's going to be x minus 4. Now I know since we're multiplying conjugates, that the middle term should cancel out. So I'm going to play with this to where I have conjugates with the purple and the green. And so the green is going to become x minus 4 plus I. And the purple is going to become x minus 4 minus I. And the way I'm going to turn these into conjugates is I'm going to put x minus 4 together as one term, and I'm going to leave the minus and plus I out there. So really these purple and these greens, if I clump x minus 4 as a binomial together, we can multiply this more easily now. So I'm going to go to f of x equals x minus 4. Now, when I do this first, x minus 4 times x minus 4, we're going to get times x minus 4 squared. And I know the middle terms would cancel out, but I'm going to show you why. If I do this green x minus 4 times minus I would get minus I times x minus 4. Then when I do the green I times the purple x minus 4, we're going to get plus I times x minus 4. And if you look at this and this, those two cancel each other out. And then the last thing we're going to get is I times negative I. So we get minus I squared. So what we end up with inside those red brackets is f of x equals x minus 4 times, when I multiply x minus 4 times x minus 4, I get x squared minus 8x plus 16. And then I have minus I squared out there. These are gone. I have minus I squared, which is really plus 1. So now I'm going to simplify that red again. And I get f of x equals x minus 4 times x squared minus 8x plus 17. Now I can finish multiplying that together. So you can see this is tedious algebra, nothing you haven't had before but tedious. So f of x equals x cubed minus 8x squared plus 17x minus 4x squared plus 32x minus 68. And then finish simplifying it. So f of x equals x cubed minus 12x squared plus 49x minus 68. And that would be the least degree polynomial that you could have if you have 3 solutions. And that's another practice on that. So the only thing we need to talk about from section 5.8 are how can you even decide what possible rational roots you might have. And if I don't give you a factor to start with and I don't give you a 0 to start with, where do you start and how do you start to factor that polynomial? So this is called the rational zero theorem, and before graphing calculators it was an incredibly tedious problem to figure out what factors might be if you have a third, fourth, fifth degree polynomial equation. But in order to figure out the possible factors that could exist, you look at the constant term and you look at the lead coefficients. So in this case, and anything that is a factor of the, so p is equal to our constant term, and q is our lead coefficient. Oh, I'm not going to finish writing that. And so anything that might be a factor could be any of the factors of p divided by any of the factors of q. So in this nightmare of a problem, if I ask for all of the possible rational zeros, you'd say, okay, well, p equals 40, and all possible factors of 40 are, you can have plus or minus 1, plus or minus 2, because remember, if you're multiplying together to get 40, you can take negative 1 times negative 40, and that gives you 40. So negatives aren't excluded from this. And then you get plus or minus 4, plus or minus 5, plus or minus 8, plus or minus 10, plus or minus 20, plus or minus 40. This is a really bad example to start off with. And then q is equal to 6. And so all of the factors of 6 would be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So if you look at all the possible combinations you could have of things that might be factors, you can say it'd be 1 over 1, or plus or minus 2 over 1, or plus or minus 4 over 1. And we have a million different factors that we could check to see if it goes into it. Now this is where you would use your graphing calculator and put it in and see where it looks like it's crossing the x-axis to figure out where you want to begin to test these factors. Because obviously you don't want to test, this would produce 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This would produce 24 things that you could check with synthetic division, and that's too tedious. So list all possible rational zeros of f of x equals 3x to the fourth minus x cubed plus 4. Well, in this case, p is equal to 4 and q is equal to 3. This is much more manageable. So our factors of 4 would be plus or minus 1, plus or minus 2, and plus or minus 4. Our factors of 3 are just plus or minus 1 and plus or minus 3. So to figure out all possible rational zeros, you can say you'd have all of the factors of p over 1, and so those would yield plus or minus 1, plus or minus 2, and plus or minus 4. And then the other ones would be all of those factors of p over the other factors of q. So you have plus or minus 1/3, plus or minus 2/3, and plus or minus 4/3. So this one would yield 12 different things that you would need to check using synthetic division to see if there are any factors. And remember, when you use synthetic division, if there's no remainder, that means that that particular number is a factor of that polynomial. So this was the same one pretty much. List all possible rational zeros for this one. So in this case, we have P equals negative 15 and Q equals 1. Well, this one's really easy to find the possible rational zeros because the factors of P are plus or minus 1, plus or minus 3, plus or minus 5, and plus or minus 15. Well, the only factor of 1 is plus or minus 1. So these are it, because if you put any of these over 1, those are the 8 values that you would check to see if it was indeed a factor. Okay, so now let's find all the zeros for this. And so in this case, we have that P is 30, and you have Q is equal to 1. And so to find the possible rational zeros, since Q is 1, it's going to be the factors of P. And so in this case, it's going to be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 5, plus or minus 6, plus or minus 10, plus or minus 15, and plus or minus 30. So not real fun, which is why we're going to go to our graphing calculators now to check this. So I put the function into my calculator, and I got that, and the graph is actually going to reveal all the roots to us, which is really nice. But I'm only going to look at one of them. I'm going to look at negative 5, and I'm going to start with that to show you what you do if it didn't look so pretty. So I know that negative 5 is one of our roots. And so I'm going to plug that in using synthetic division and say 1, 1, negative 19, 11, and 30. And I know it's going to go in evenly. So 1, negative 5, negative 4, 20, 1, negative 5, 6, negative 30, 0. So what this tells me is this is our constant, this is our linear, this is our quadratic, that's our cubic. And so we now have x plus 5 times x cubed minus 4x plus squared plus x plus 6. Well, we continue on from here and go back to the graphing calculator and say, okay, well, negative 1 is also one of our roots. And so I'm going to go back here, and I'm going to continue from here. This is what I need to use now. And so I'm going to say negative 1. And that's going to go into 1, negative 4, 1, 6. And so that's basically breaking down this cubic. So when I do that, I get 1, negative 1, negative 5, 5, 6, negative 6, 0. That's 6. So now I have x plus 5 times x plus 1. And now I have this quadratic. There's my constant, there's my linear, there's my quadratic term. So it's going to be x squared minus 5x plus 6. Now I have it broken down to a quadratic, so I really don't need to use synthetic division anymore. So I know I have x plus 5 times x plus 1 times, and then this quadratic will factor to x minus 2 times x minus 3. So our other two roots should be 2 and 3. And if I go back to the graph and look at it, sure enough, it crosses the x-axis at 2 and 3. So that's how the algebra ties right into this. So we are going to be looking at factoring completely. And in this case, the zeros would be negative 5, negative 1, 2, and 3. And that's it.